goes through the point P. And so to get there, we can show that if we draw this other line in, then we can see that the angles will not add up to, or they won't be right angles. And so if both the angles add up to something that's less than 180 degrees, then we can see that it's that we're going to have an intersection, in this case on the right side. And you can see if we do the same thing on the left side, we'll have an intersection on the left side. And so this isn't a comprehensive proof by any means, but you can see where we can show that there's only going to be one parallel line that exists. And if we alter that at all, then we're going to have an intersection. And so to show that Playfair's axiom implies the parallel postulate, we can construct kind of a similar situation. And so if we have a line L again and a point P not on L, Playfair's axiom tells us that there's exactly one line through P that is parallel to L. So again, we kind of play this similar game of checking to see what happens when the angles between the two lines are less than 180 degrees. And this kind of seems a little circular, but there are some nuances where if we kind of reorder the way in which we do things, we can use Playfair's axiom to imply the parallel postulate. And so above we can see that if the two angles alpha and beta are less than 180 degrees, then the lines M and L are going to meet on the right side. And if alpha prime and beta prime are less than 180 degrees, then the lines are going to meet on the left side. And so that tells us that that M is only going to be parallel to L if and only if the two angles add up exactly to 180 degrees. And this is kind of using Euclid's fourth postulate, which says that all right angles are equal to one another. And so again, so some of the historical significance of this is that it's really easy, or I guess not really easy, but it's easier to imply a lot of equivalencies to the parallel postulate, but it's a lot harder to prove the parallel postulate itself. And so if we can show, again, that Playfair's axiom is equivalent to the parallel postulate, Playfair's axiom happens to be a bit easier to prove. So it's simpler and a bit easier to understand.
Okay, so I'm looking, oh, okay. I'm just.
Oh, I have my mic muted, I think.
Oh, okay.
Yeah, okay, sorry. Yeah. Another thing we found, which relates to Playfair's axiom and also proposition 30 of Euclid. Mm-hmm. So it's not directly the parallel postulate, but proposition 30 says that two lines, each parallel to a third, are parallel to each other, which is logically equivalent to Playfair's axiom. So if you just let X be like the set of all distinct pairs of lines which meet, and Y be the distinct pairs of lines which are parallel to a common line, and then just let Z, a lowercase c, be just a single pair of distinct lines, then you can see that for all Z, like if Z is in X, then Z is not in Y, which is Playfair's axiom, and its logically equivalent contrapositive would be for all Z, if Z is in Y, then Z is not in X. So, which is Euclid's 30th proposition. And then in simpler terms of more like, you know, De Morgan stuff, it's just no X is Y and no Y is X.
Okay. Good.
And these are the sources for some of the visuals we used earlier in the presentation. So.
Good. Okay. I assume you're done? So I just had a couple of questions. Could you go back to the postulate slides? It's not really a question, but because all the, you know, that lists all the postulate and definitions. Okay, yes. There we go, good. That one perfectly. Yeah, like I just wanted to point out here for the first, let me go back to the definitions. You know, the fact in definition 3 that he talks about the ends of lines being points, that kind of I think reflects that sort of potential infinity, that he speaks of these lines as ending. I'm not quite sure what he means by that, but he does talks about the ends of the lines as points. My understanding has always been that line and a line segment get mixed up. That the term can be used for both, but generally he's talking about line segments. Definition 4, I've never, I'd like, it'd be fun to try to describe a straight line geometrically, and I don't know. I mean, I that's another one I've never quite figured out exactly why that is, why that's a definition or not. Like, what does it mean to lie evenly on itself? Does it mean not to curve? So I don't know. So I've had a good, I don't know. I thought about that, and I still haven't. I don't really know that you can do a definition that's going to be better than that, but I just think it's a really hard thing to define. And so what happens in some geometries is they don't define what a line is. It's kind of an undefined concept, and that happens sometimes in mathematics. It just has certain properties but not definitions. So that I think number 4 is why some people use lines as undefined objects that are only defined by a list of properties. So I wanted to point that out. Postulate 1, that's our straight edge. We can draw a line from any point to any point. That's why this is straight edge geometry. That's your tool. And number 2 is that you can produce it as long as you need to. Again, think back what Aristotle was saying about potential infinity. Number 3 gives us the ability to draw a circle. And so 1 and 3 are really the things that in this book of Euclid are really the key to everything. Those are the 2 tools you have to make things. And again, I don't need to say anything more about those things. So I wanted to say that, wanted to point that out. I think it's important. And then I had a question. Somebody was suggesting, I don't know a whole lot about Playfair, and I haven't made a detailed study of him, but did I hear somebody saying that one reason that Playfair simplified things was because was for his investigation about how postulate 5 fit in with the other 4? Did I hear that right?
Yeah. So I'm not sure if Playfair himself said this, but I believe Playfair's axiom was a lot easier to prove.
Yeah. Or to use.
So there were some suggestions to just kind of switch out postulate 5 with his axiom.
Right. Yeah, and but I guess my question was he also investigating that question of the role of postulate 5 within Euclid?
I'm not sure, but I think that was the case. Yeah.
Okay, that's what it sounded like, the implication. Again, I don't know a whole lot about him, so I was curious about that. Okay, anyway, good. Okay, so that was good. I like bringing in that postulate 30 and bringing in some additional context for that. So again, that was good. And again, it's just amazing to me to think about that, how much math was spawned by that postulate. And we'll talk about that a little bit later in the course. Okay, that's all I got to say about that. So how about the 4th group? You all ready?
Sure.
Okay, so whenever you're ready to go, I'll let you get set up. Okay.
Bryce, do you want to share it or do you want me to?
I can take care of it. Just give me like half a second. Okay, can everyone see?
I can see it.
Sounds good.
All right.
Oh.
So we're going to be talking about Euclid's infinitude of primes. So Euclid proposed that there were a finite number, or there were more than a finite number of prime numbers, and that they're infinitely many prime numbers. He originally published this idea in Elements around 300 BCE. And the infinite primes theorem is not mentioned again in Elements, so it kind of stands alone. His claim was that if P1 to Pn are prime numbers and m is equal to P1 times P2 times Pn plus 1, then none of P1 Pn will divide m. So this proof also appears in several other places and has several other applications, including like Dirichlet's theorems, prime number theorem, and Euclid numbers. And just a little bit more Euclid numbers. So a Euclid number is an integer in the form of En equals Pn plus 1, where Pn is the nth primorial, aka the product of the first n prime numbers. And it has been stated that Euclid's proof for the infinitude of primes relied on these Euclid numbers, but that is false. Rather than beginning with the assumption that the set of all primes is finite, Euclid considered infinite primes. And just some general properties of Euclid numbers is that not all Euclid numbers are prime. For every Euclid number is congruent to 3 mod 4. And for n is greater than or equal to 3, the last digit of the Euclid number is 1.
So there's a couple different ways that you can prove it. There's like the original geometric proof, but then there's more simplified version, which is more analogous to what we would use nowadays, which is the algebraic proof. So the algebraic proof relies upon you have a finite set of prime numbers, P1 through Pn, and they're all prime. And then you construct a primordial from that, which you multiply all those prime numbers together, and then you add 1 to it. And these prime numbers don't necessarily have to be the first n prime numbers or like continuous prime numbers. You can go like 2, 3, 7. And to move forward, we're also going to use the fact that you have the equation. You have A equals JB plus R, where and for this we're going to assume A is M, and then JB multiplied all together is your series of P1 through Pn, but we're going to pull one of those prime numbers out, and that's going to become B, and then you're going to add R, where R is 1. The thing is using this equation, B is only going to divide A if A divides R. The thing is, A is never going to divide R because R is 1, and nothing is going to divide 1 except 1, and we know M isn't 1. Therefore, no matter what B we pick from that set of primes, B is not going to divide A, which means that none of those prime numbers in that set that we picked are going to divide M. Now we know that, of course, M is either prime or composite. So if M is composite, then any prime dividing it, then there has to be some prime dividing it because of it's going to have some sort of prime number decomposition. But it's not divisible by P1 through Pn because of what we just proved using A equals JB plus R. Therefore, there's going to be some sort of prime that isn't in that set, meaning that that finite set of primes is not all primes. And then if M is prime, obviously, that's an additional prime. So the thing is how this proves that there is an infinite set of number of primes is that no matter how large of a finite set of primes you use to construct M, there's always either going to be another prime that divides M, or M itself is going to be prime. And therefore, there's always going to be more primes no matter how big you make this set.
Okay, and here is a geometric way of looking at the proof. So you start out with these line segments, and you have A, B, and C, which are all prime numbers. And in this world, we're going to say that A, B, and C are the only prime numbers. And then you have the segment DE, which is the product of all prime numbers and therefore is divisible by A, B, and C. And then you add on df onto de, and that is a unit. So it's a 1. And then to continue, the segment EF can either be prime or composite. And if it's prime, then that shows that there are more primes than just A, B, and C, which proves that there will keep being more primes and there are infinite many primes. So then the other option is that EF is composite. So if it's composite, like Bryce says, it has to be divided by a prime number, which we will call G. And then since DE is defined by being divisible by all prime numbers, it must also be divided by G. And since G divides EF and DE, it must also divide the remainder DF, which would be impossible because DF is 1, which cannot be a prime number. So to make this work, G has to be a different prime number from A, B, and C, and so there must be more primes.
Okay, so the geometric proof can be used as a visual example of Euclid numbers where the segments A, B, and C can represent the first 3 primes, 2, 3, 5, and then EF would be the third Euclid number, 31. You could create the same proof with all the Euclid numbers, and they also show that there are infinite amount of prime numbers. But other numbers can be used in this proof too. For example, A, B, and C could be 3, 5, and 7, which would make EF 86, which is not a Euclid number. But it still shows that other primes exist besides the 3 that were given. Therefore, the proof doesn't rely on Euclid numbers. Also, Euclid's proof doesn't say that EF will always be able to be prime. This means that it is unknown if there are an infinite amount of prime Euclid numbers. And this is currently an unsolved problem in mathematics.
Okay, that's the presentation.
Good. Okay. Again, a nice job. I'm going to just share. You should see at least one Euclid thing here. So I'm going to show you. Let's see, which one do we want? This one. Okay. Oops. Yeah. Okay. I think I might have shared the wrong thing. Is this Euclid's Elements book 9, or did I share a different Euclid?
Well, that's the right thing.
I'm sorry?
That's the right thing.
Oh, okay, good. Because I had 2 open and I thought it was something else. Okay. So I just don't like the fact that I don't see what you see. Okay. So I just have to get it where I can see it. You're able to see the whole thing. I mean, this is pretty remarkable. Now remember, Euclid was written in Greek, and maybe in Alexandria in 300 BCE, and then, you know, the version the earliest version we have is from like 800, CE. So, 1100 years later, and then somewhere in the 1800s, Thomas Heath, and like a Victorian British guy, translated it into English, and so that's what we're looking at it, and it sounds stodgy. I mean, because the prose is kind of it's kind of anachronistic in some way. So what we're seeing is not what Euclid did necessarily, but it's supposed to be close to his spirit. And I like the stodginess of it, even though it makes it hard to read because that makes it sound old. But the remarkable thing here is there's no numbers. And I just think that you can have this proof about prime numbers with only using geometrical magnitudes. I think is pretty amazing. And so and this is based on Greek number theory, which again the commentators believe that goes back to Pythagoras, because it's this notion of playing with numbers. And no one knows how old this proof actually is, but there's some thought that it does go back to something that the Pythagoreans might have known. And I think Molly pointed this out, and it's a really good thing to point out. When this proof is presented today, almost always it says, let the number of primes be finite. And then you produce, and therefore there's n primes. And then you produce one more, so your argument, your statement that there were only n is false. And this avoids the whole thing about infinity. There's nothing about infinity in this one. It just says if you have a group of primes, you can always find one more. And again, this has to do with infinity wasn't sort of investigated the way that we might investigate it back then, at least what people can say. But it's really important, I think, to point that out. That, you know, I think that was a good point that Molly made. That infinity, that you know, Euclid never says assume they're finite. He just says here's three. We can always find another one that's not one of those three. So anyway, so. I had one more. I think I had one more thing to say. One more question to make. Oh, never mind. It was answered. I had a question about why Euclid numbers weren't involved, but Nick did a good job of answering that. Okay, good. So again, very good jobs today. I was impressed with the presentations. As I said, we'll have this like sort of a different kind of project with Archimedes, which will be paper-based, and then the next presentation will be based on non-Western math, and I'm still figuring out how that one's going to go. But it's probably like, you know, I probably will give it out for two or three weeks. Okay, so that's all I have. Any questions or comments? Again, I'm gonna. Oh, go ahead. I thought somebody was saying something, but I'll send out rubrics. I'm going to ask a couple of different questions, but I'll send out something very similar to what I sent out before. Okay, so that's all I have. So if any questions or anything, if not, then have a very nice weekend.
Have a good weekend.
Yep, you too, everybody. Yep.
Good weekend, Dr. Alexander.
Thank you. Okay, Colin, I don't know if you're still here or wanted to say something, but I was going to log out. Just wanted to check to see if you wanted to talk or something. Okay.